All right, this is our final component to learn in the linear regressions. And that is, kind of actually did this a little backwards. We learned how to run a test, we learned how to do an interval, we learned how to do that inference, but we actually need to talk about what conditions need to happen, what assumptions need to be made in order for us to actually be allowed to do those two things that we just did, the tests and the intervals. All right. So that's what we're going to talk about today. In the past, all of our conditions have been based on getting real, checking for randomness, checking that independence, and checking to see that the sample size was large enough. Or in the case of chi-squared, that we had the expected counts were large enough. All right, this is a little more complex because we are not verifying that the normal model applies or the approximately normal model applies, or that a chi-squared distribution applies. We're going to do these conditions to verify that a linear model is appropriate, a linear model applies, and so there's some sort of linearity happening. So we can then go investigate more specifics. So do we have that evidence to say, yes, the linear model does definitely apply, or yes, here's the estimate for that slope's value. Okay, here we go. So here is a problem that we are talking about education versus income. So we're actually talking about income as the explanatory variable. I wonder if I wrote this wrong. This says income is the explanatory variable. But let's look down here to see if income is really the X. Haha, look at that. I did that wrong. Because look at these. Education is the X and income is the Y. That makes sense. So I can tell I had a mistake right here. This should say education because education's X. All right, but regardless, we'll keep going. We actually don't use these numbers when we're having our discussion, except for the correlation coefficient. Okay, 57 pieces of data. Is education a good predictor of income? So the conditions that we do are the randomness, okay, and we do have independence, but then we have a few other ones. So we're going to use the mnemonic device R-line, R-L-I-N-E. Now, some people call it liner, L-I-N-E-R, but I think we've been putting randomness first, so I just would say R-line. Okay, let's do our R-line. So let's talk about what each of these things is. Of course, the R is that randomness. So are these data, subjects, are they selected randomly? Or if it was an experiment, are they randomly assigned to their treatment group? Then you are stating those. Okay? I don't have a picture that will represent that. We just are reading that in our information. Linearity. L for the LR line is linearity. So we are checking to see that the general shape of the data, it's just a rough estimate, that the general shape is linear and that there's a correlation coefficient that's somewhat moderately strong. So in this case, our square root of r squared, the square root of 0.329 is 0.57. So the words I would say here is, yes, the data appears to be in a positive linear direction with a correlation coefficient that is moderately strong, positive linear relationship. So that's what I would write there. I in the line is the independence. No picture to discuss that. That is, if it's a sample from the population without replacement, then is our sample less than 10% of the population, so it's not affecting the probability. Or, we can say the data is representative of the population that it's coming from. The data pieces are not changing the other pieces, so they're not affecting the others. Okay, that's your independence. Now, these last two are pretty new, kind of, and in some cases, abstract type topics. So let's discuss them. N stands for normal probability plot. So what we are doing for this normal probability plot, here's what it might look like. So I have got these dots were all kind of arranged. If you look very carefully, it's hard to see, but the x-axis says normal scores or the z-scores. I guess if it's means, it'd really kind of be t-scores. But I don't know. It says normal. So, all right. So there's that. And then residuals are over here. So what this is saying is this. I want you to take a look over here on the graph to the right. These red lines here represent a residual of 0. Okay, so this residual of 0 right here. And then a residual of 0 with a z-score of 0. So a residual of 0 and a z-score of 0. So that right there is a point that is exactly on the prediction line. So that's the amount of data that was exactly as predicted because it had a z-score of 0 and a residual of 0. Okay. Now, how much data is within one standard deviation of the residuals away from what it was predicted to be? So we want to see that approximately 68% of our data was within one standard deviation. So see, look, I have my little purple section drawn from a -1 z-score to a +1 z-score. Was in with one of these standard deviations away from what it was predicted to be. All right, and then next is that then we have about 95% of the data. See, most of it then, see, it's less dense here. Okay, so we've got some other more data out here. So there's 95% of the data within 2 standard deviations of what it's predicted to be, and so on, and then 99.7 for those 3. So we're looking for, this more density in this middle and less dense as we get further out. And this should be a somewhat straight line. A somewhat straight line is telling me that you have some that are about the same amount that are above the line as that are below the line, have positive z-scores and having negative z-scores. Okay, so that's what we're looking for with this normal probability plot. Here's the language we kind of say. I can see from the graph, whichever, I'd label it and I say graph B or whatever, that the residuals are approximately normally distributed. That's kind of what I'm wanting to check to see if the residuals are approximately normally distributed. That kind of is the key language that I'm stating there. All right, and the last one. E stands for equal variance in the residual plot. So you need to find the graph that is given to you because almost certainly these graphs will be given to you. I mean, a long time ago, I would have my students go through the process of making these graphs, okay? But I have since learned that it's more about can you interpret and do you know what these graphs are saying and what they are implying about the inference rather than having to go through the technical components of making these graphs. So I'm pretty sure they'll be given to you. So equal variance. So we go to the residual plot. So you see this has residuals here on the left and then that predicted income on the bottom. So here is our residual plot. We have equal variance if the residuals are about the same distance above and below the prediction line throughout the entire domain of the line. So here's what would be bad. This would not show equal variance. If we started out close to the line, but as we got farther along in the x direction, so we got farther away, our data fanned out. That is not equally varied residuals. Okay, so we're going to check and see that the residuals are equally varied, and do not depend on x. They're not changing based on their location in the domain. And then, of course, we'll finish this out by saying a linear model applies. That will be our conclusion. All right, so there it is. Let's practice one. Here we go. So Old Faithful isn't all that faithful. Okay, so the eruptions have, the length of the eruptions vary greatly depending on the duration or how long it has been since its previous eruption. Create a 98% confidence interval for the slope of the relationship between the duration, so how long the eruption lasts, and as a result of how long that eruption lasts, will it affect the interval, how long it takes then for another eruption to occur, the interval between the eruptions. A regression analysis is based on a simple random sample of 225 eruptions. So let's take a look at this. We're going to do our line for our assumptions. So what I did was I took a look at the graphs. See how the graphs are over here on the right-hand side. I'm first going to label those. Just call them graph A, graph B, and graph C. Okay, those will inevitably be given to you. But you do need to know which one is demonstrating what. So before we get into all of the information that we specifically write, let's take a look at graph A. Graph A has just got the duration is the x and the interval is y. So I can tell this one is just a straight up XY graph. Graph B has the number of eruptions, okay? And then these residuals. So these are the residuals. So all this data here, that means most of the data was right here around what it was predicted to be, had a residual of around 0. And the farther you got away from the prediction line, the less data you had. So you had less data farther away from the prediction line as you got farther away. So the idea is we're looking to see that these residuals are approximately normally distributed. So this graph is going to go with normal probability plot. Okay, so I'm thinking in my brain about that. Now let's take a look at this last graph. Okay, this one has the predicted minutes, and this is the residual. See this 0 here in the center? So there is the prediction line. So when I have this prediction line, this LSRL right here, I want to see that the residuals are equally varied on either side of that LSRL. Equal variance in the residuals. Equal variance in those residuals. So there's no fanning out of those residuals like I showed you down here. That would have been bad. Okay, so here we go. Let's look at how we kind of write these. Now, some of these things are kind of canned phrases that you can remember of how to do them. So first, random. Stated random sample of 225 eruptions. Okay, done. Here we go. Linearity. Graph A shows a linear shape and R equals 0.88. Where did I get that? Well, I square rooted that. shows a strong positive linear relationship between duration and interval. So I'm interpreting that correlation coefficient. Independent. Each eruption is independent of the other eruptions. So we're saying the eruptions themselves are independent, but yet that interval between the eruptions is what we're referencing, what we're investigating. All right, so R line. We did R for random, L for linearity, I for independent. N and E are the next two. So N, normal probability plot. So normal, that's saying, so I need to say something about the residuals are approximately normally distributed. Okay, so something along those lines. Let's see. Okay, graph B shows that the residuals are approximately normally distributed. That's pretty much what you're going to be saying every single time. Just find the correct graph and reference the graph that demonstrates that. Graph B shows the residuals are approximately normally distributed. And then E is showing E of this equal variance in the residual plot. So I'm saying graph C shows that the residuals are equally varied along the entire LSRL, or along the entire domain, the x values of the LSRL. So you're pretty much just going to be saying that. Equally varied on either side of the LSRL for the entire domain. All right, and conclude with the linear model applies. That's it. That's a skeleton or an outline of what you're doing every time for your assumptions. So you're now going to practice that. I think I just have you practicing it once on the assignment, and then you go through and then you do some additional problems besides that. So hopefully once is enough practice for you, because we aren't practicing it a ton, but you need to make sure you get that wording right. Okay, so good luck to you on your Day 4 assignment on the inference with linear regressions, including their assumptions.